For about 140 years, the car industry has sold us the same bedtime story. Your suspension is sophisticated. Luxury brands whisper it with polished marketing, adaptive magic, intelligent, as if some invisible genius is protecting you from the road. But strip away the vocabulary and what's left is almost embarrassing. Most modern suspensions, yes, even on six-figure cars, are still doing the same primitive thing. A Victorian carriage did. They get hit first, then they react. That's the core problem. It's a reaction system, not a control system. The tire meets a bump, the spring compresses, the damper tries to calm the chaos, and only then does the car attempt to restore order. By the time your suspension responds, the damage to comfort, grip, and stability has already happened. And here's why the industry hasn't escaped it. It's not a software limitation. It's physics. Traditional dampers rely on fluid moving through tiny passages, valves, and pressure changes. That means hysteresis, a built-in delay caused by viscosity, heat, and flow resistance. The faster the road hits you, the more your system becomes a compromised machine. You want a softer ride, you lose control. You want sharper handling, you sacrifice comfort. The industry calls it balance, like it's a design philosophy. But what if that trade-off was never a truth? Just a trap we got used to. Because if your suspension only reacts after impact, then it's always late, always behind, always negotiating with the road instead of commanding it. And once you see that, the uncomfortable question appears. Have we been driving 21st century cars with 19th century chassis logic? Here's the part that makes this even more uncomfortable. The future suspension isn't new. It's been haunting the industry for decades, showing up, proving it works, and then getting buried. In the early 1990s, Formula One accidentally exposed the secret. Williams built the FW14B with active suspension, and the car didn't just look fast, it looked unfair. It could keep the chassis level, control pitch and roll, and make the tire contact patch behave like it was glued to the track. The performance gap got so ridiculous that the sport did what it always does. When technology becomes too dominant, it banned it. Then came one of the most famous, almost revolutions in automotive engineering, Bose. Yes, that Bose. Dr. Amar Bose spent years building a suspension concept that sounded impossible. Replace a passive damper with an electromagnetic actuator that can push or pull the wheel on command. In demos, the car could absorb bumps like they didn't exist. It could corner with near-zero body roll. It looked like the chassis had its own brain. So why didn't it change the world? Because the world it needed didn't exist yet. To actively move a wheel, you need serious power, fast, repeatable, and continuous. The old automotive electrical ecosystem, 12-volt architectures, alternators, and engines optimized for fuel economy, was never designed to feed a high-demand actuator at each corner of the car. Even if the technology worked, it was heavy, complex, and brutally expensive in the context of that era. The best ideas were trapped behind a simple wall energy. And that's the context people miss when they ask, why didn't we have this earlier? We didn't have the platform, but now we do. Because once high-voltage EV systems arrived, 400 volts, 800 volts, silicon carbide inverters, high-density battery packs, the rules changed. Suddenly, delivering tens of kilowatts isn't science fiction. It's just another line item in the power budget. So the real story isn't that someone invented a miracle suspension in 2026. The real story is that the automotive world finally built the electrical backbone powerful enough to let a decades-old idea escape the lab and enter the street. Now we're at the point where the story stops being philosophy and turns into hardware. Because what BYD is showing with DiSus Z isn't a better shock absorber. It's a different category of system, and the easiest way to understand that is to start with what it is not. It is not an air suspension trick. Air suspension can raise or lower the car, soften or stiffen the ride, and feel impressively luxury. But at its core, it still behaves like a balloon with plumbing. Air has compressibility, valves have flow limits, and the whole system has inertia. It can adjust, but it's not built for instant force-precise control at the millisecond level. DiSus Z aims at that millisecond level. Instead of relying on pressure and fluid resistance, it uses a linear electromagnetic motor at each corner. Think of it as a push-pull actuator that can generate force directly in both directions on command. Not resist motion after it happens, but create motion before the chassis loses control. It's the difference between a door closer that slows a slam and a hand that catches the door before it ever slams. That's why the reaction time claim matters. When a system talks about operating around 10 milliseconds, it's not a marketing flex. It's the practical threshold where the suspension stops being late. For context, a human blink is roughly on the order of a tenth of a second. Brain-to-muscle reactions are slower. Meanwhile, the road doesn't wait for you. At highway speed, a bump arrives and ends in a heartbeat. So the question becomes, if you can generate corrective force within a few milliseconds, what do you do with that power? You use it to rewrite the oldest assumption in chassis engineering: you must choose between comfort and handling. Because that trade-off exists mainly when your system can only dissipate energy, turn motion into heat after the fact. Passive dampers are fundamentally energy sinks. They cannot add energy strategically to maintain an ideal body posture. They can only resist and absorb. A true active actuator can do the opposite. It can add or subtract force at exactly the right moment to keep the body stable, even while the wheels experience chaos underneath. This is where the old skyhook idea comes in. Imagine the car body is attached to an invisible hook in the sky, an unmoving reference point. The wheels bounce, the road gets ugly, but the cabin stays calm because the system is actively working to keep the mass of the chassis anchored. And once you frame it that way, you see why the road feels different. The suspension isn't negotiating, it's enforcing. There's another debate DiSus Z pokes a finger into: unsprung mass. Traditionally, engineers fear adding weight to the wheel side of the suspension because heavier unsprung mass is harder to control. The wheel follows bumps less cleanly, and the tire loses contact more easily. But that fear assumes a passive system. With an actuator that can generate strong, fast force, the game changes. Instead of the wheel getting thrown by the road and the damper trying to calm it, later the system can actively manage wheel motion, keeping tire load more consistent. In other words, the actuator isn't just surviving the physics, it's fighting back against it. And this is where the most disturbing implication emerges. If an active suspension can push the wheel down fast enough, it's not only improving comfort, it's directly shaping grip. Gravity presses the tire into the road at 1G, but an actuator can spike vertical force transiently, meaning it can increase tire load faster than gravity alone would. In a simplified sense, you can think of it like generating downforce without needing aerodynamic speed. Not permanent, not magic, but rapid force control at the contact patch. If you're from the old world of chassis tuning, that sounds like heresy. Handling has always been about springs, dampers, anti-roll bars, geometry, and above all, compromise. You pick a personality for the car, then you live with the consequences. DiSus Z suggests a different future. The personality isn't welded into metal. It's computed, and if it's computed, it can change. Which means the real breakthrough isn't that the car can float over bumps. The breakthrough is that the suspension is finally stepping out of the 19th century job description and absorb impact and into a 21st century role real-time control of body motion. If DiSus Z is the philosophical brake suspension as real-time control, then DiSus X is where BYD turns that control into a weapon. Most people first saw through a viral moment a car that can jump. It's the kind of demo that makes headlines and triggers disbelief because it looks like a party trick from a sci-fi movie. But the jump is not the story. It's the proof of power. The story is what that power enables when the situation is not a showroom stunt, but a real-world emergency. BYD's pitch here is brutal in its simplicity. If you can generate massive force fast enough, the chassis stops being a passive object that endures chaos and becomes an active system that survives it. One of the numbers that frames this is the claimed peak power devoted to the suspension around 36 kilowatts. Put that into perspective. Traditional suspension components don't consume power in that sense. They dissipate energy. They don't have a power budget like a motor. An active suspension does. And when you're talking tens of kilowatts, you're no longer in the world of subtle correction. You're in the world of rapid high-force intervention. But intervention depends on the electrical backbone. This is where 800 volts architecture and silicon carbide, SiC, stop being EV buzzwords and start being weapons-grade enablers. High voltage means lower current for the same power, less heat, less loss, and faster delivery. SiC power electronics can switch more efficiently at high frequencies and high temperatures. Together, they make instant power less mythical and more repeatable. So what does BYD claim you can do with that repeatable instant power? They don't just talk about comfort. They talk about redundancy, what happens when the car loses a wheel, or a tire explodes, or a corner is suddenly compromised at speed. In the old mechanical world, that's where physics wins. You can stabilize with brakes and steering, but you're still fighting a chassis that's already collapsing on one side. In the DiSus X world, the chassis can fight back. The system narrative goes like this: detect the event, then reconfigure the car's posture immediately. Retract or control that damaged corner, stiffen the opposite diagonal corners, redistribute load, and keep the vehicle tracking straight, long enough for the driver or the control system to regain stability. That's why the jump demo matters. Not because anyone needs a car that hops, but because it telegraphs the ceiling. The suspension can create enough vertical acceleration to momentarily lift mass. If it can do that, then in normal driving, it has a terrifying amount of headroom for corrective force. And here's where the insult lands on legacy systems. In the Western premium world, we've seen incremental steps 48 volts, active anti-roll clever dampers, faster valves, better algorithms. They're improvements, but they're still fighting the same fundamental limits of fluid dynamics and small power budgets. A 48-volt system is like bringing a pocket knife to a gunfight if the other side is running an 800-volt powertrain with high-frequency power electronics and a suspension that thinks in milliseconds. So DiSus X isn't selling better ride quality. It's quietly selling a new definition of safety. When things go wrong at speed, the car doesn't just react. It reconfigures. After DiSus Z and X, it would be easy to assume BYD's message is simply electric motors everywhere. But DiSus P is a reminder that the revolution isn't married to one actuator type. It's married to one idea. The chassis becomes programmable. DiSus P leans into hydraulics not as an old-school compromise, but as a deliberate choice for scenarios where you want massive travel, heavy load management, and strong continuous force. Instead of one passive damper per corner, the system behaves more like a coordinated network pressure flow and control logic working together across the vehicle. The key claim here is multi-axis control. Not just soft or stiff, but the ability to manage pitch, roll, and heave as a dynamic posture problem without relying on a traditional mechanical anti-roll bar as the primary crutch. In plain terms, the vehicle isn't merely absorbing bumps. It is deciding how it should sit, lean, and move in real time. On-road, the system narrative is about stability. When speed rises or the car detects aggressive inputs, DiSus P can raise effective stiffness. Dramatically, figures like up to 200% get used as shorthand for how much authority it can apply. That's the performance side, reducing unwanted body movement, keeping a more controlled platform for steering and braking. But off-road is where DiSus P is positioned as something different, not comfort tech, but capability tech. BYD highlights articulation numbers like 155 millimeters, get used to signal how much wheel travel and wheel independence the system can support. And that matters because off-road traction isn't about horsepower. It's about keeping tires on the ground when the terrain tries to lift them off. More travel, smarter load distribution, and faster posture correction means the vehicle can maintain contact where traditional setups start to lift wheels and lose grip. Then come the utility demos, the ones that look flashy, but are meant to sell the idea that the chassis can perform tasks, not just handle road input. You see sequences like a float mode concept, adjusting posture to reduce harsh impact. You see tank turn style movements, the chassis cooperating with drivetrain control to rotate within a tight space. You see the dramatic one. The vehicle can raise a wheel to help with tire changes, turning the suspension into a lifting device. In a legacy vehicle, these functions require external tools, jacks, manual intervention, specialized equipment. In the DiSus P narrative, the vehicle carries its own mechanical agency. And that's the deeper point. Once the chassis is treated like a controlled system, rather than a passive set of components, the car stops being a rigid object and starts behaving like a machine that can reposition itself. So while DiSus Z sells precision and DiSus X sells survival, DiSus P sells something that hits a very American nerve utility at scale. This is the world of heavy SUVs, tow ratings, uneven terrain, and real-life use cases, where the chassis isn't just a comfort layer, it's the difference between continuing and getting stuck. Here's where the comparison gets uncomfortable, especially if you're thinking from a US buyer's lens. In the Western premium world, the best chassis tech has often meant clever ways to reduce roll and mass compromises, active anti-roll bars, faster, adaptive dampers, smarter stability control, and the occasional 48-volt subsystem to power it. On paper, it sounds advanced. In reality, it's still an upgrade path inside the same old category: managed body motion, with limited power and mostly passive hardware. That's why the voltage numbers matter more than brand names. A 48-volt active roll system can generate useful corrective torque, but it lives inside a tight electrical envelope. You don't have the same headroom. You don't have the same response authority. You're optimizing constraints. Meanwhile, an 800-volt platform designed to deliver high repeatable power for propulsion can treat chassis actuation as a parallel mission, something that can demand real kilowatts without collapsing the system. And once that's true, the hierarchy flips. The question stops being who tunes the best ride and becomes who has the power and control architecture to command the tire contact patch in real time. That's not just a European sports sedan problem, it's a very American one. Because the US market runs on heavy realities, full-size trucks, big SUVs towing uneven roads, and long-distance high-speed driving. We've built our identity around durability and capability. But if capability increasingly depends on software-defined chassis control, and that chassis control depends on power electronics and high-voltage architecture, then traditional truck toughness becomes only part of the story. Think about what the benchmark vehicles actually ask from a chassis in America. Keep a tall vehicle stable when weight shifts suddenly. Maintain traction over broken pavement at speed. Stay composed under braking with load. Protect occupants when something goes wrong unexpectedly. Legacy systems solve these problems with geometry damping compromises and stability control that intervenes after slip begins. A high-authority active system aims to solve them earlier by keeping the platform stable before the tire loses its clean relationship with the road. So the comparison isn't Chinese car versus German car. It's old chassis logic versus new chassis logic. And if the new logic is powered by high-voltage energy and fast control, then the most painful conclusion for legacy brands is this: they're not just behind in features. They're behind in the electrical foundation that makes those features real. Once you accept what high-authority active suspension really is, the implications stop being about ride quality. They become about economics, industry identity, and who controls the next definition of premium. Start with something almost poetic in its brutality. A traditional damper is a device designed to waste energy on purpose. That's literally its job. The wheel moves, the damper resists, and the motion becomes heat. It's controlled loss. The best suspension engineers in the old world became masters of that loss, how to burn energy gracefully without making the car feel broken. An active system changes the math because it doesn't have to be an energy graveyard. If you can generate force electrically, you can also do the reverse: harvest force. Instead of only dissipating vertical motion as heat, the system can behave like a generator when conditions allow closing the loop between road input and electrical energy. In principle, you're no longer just managing chaos, you're converting it into something useful. And that's where the EV chassis becomes a strategic platform, not a comfort feature. Because once the chassis is powered and controlled like a motor, it becomes tunable like a motor. The culture shift is enormous. The old world treated suspension tuning like a kind of black art springs valves, shims geometry, and engineers intuition shaped into metal. It was permanent. You bought a car, and you bought its personality. But a programmable chassis suggests something radically different. The personality can be updated. Modes aren't just sport and comfort labels anymore. They can become downloadable identities. The car can learn how you drive, adjust to the roads you live on, and evolve over time. The line between chassis engineering and software engineering collapses. The hero isn't just the tuner with perfect instincts. The hero becomes the control algorithm, the sensors, and the power electronics that deliver force precisely when needed. Now zoom out to the competitive battlefield. For decades, the West assumed the premium advantage was unassailable brand heritage, craftsmanship, mechanical refinement. The stereotype was that China could copy surfaces, but not invent the soul. A system like DiSus doesn't win because of a logo. It wins because it says, we can build the electrical and control backbone that makes the old mechanical hierarchy irrelevant. That's not a feature gap, that's a foundation gap. And foundation gaps have a nasty habit of turning into price wars, supply chain wars, and identity crises. Because if you can offer real-time chassis control at scale package inside mass production, then the question consumers ask becomes toxic to legacy brands. Why pay premium money for a platform whose core physics are still rooted in reaction and compromise? This is the part where premium quietly changes meaning. It stops being leather quality and panel gaps. It starts being control authority, how much the machine can command the physical world in milliseconds. And once premium becomes control, the geopolitical tension becomes obvious. Control requires semiconductors, power, electronics, battery supply chains, and vertical integration. The winners aren't just the companies with history. They're the companies who can secure the parts manufacture at scale and iterate software faster than the old cycle of mechanical redesign. So this isn't simply China made a better suspension. It's China making a statement about the future of the vehicle as a controlled electrical machine and daring the legacy world to defend a century of mechanical identity against an industry that now writes its advantage in code. So if you're still thinking this is about comfort, about a smoother ride over potholes, you're missing the point. This is about the moment the chassis stops being a passive collection of parts and becomes a powered control system. The kind of system that can intervene before instability becomes visible. The kind of system that doesn't just absorb the road, but reshapes how the tire meets it. And that's why the shift feels so threatening to legacy identity. Because for a century, great cars were defined by mechanical mastery. Springs, dampers, geometry, feel. Now the advantage is moving into high-voltage architecture, power electronics, sensor fusion, and control code that thinks in milliseconds. The revolution isn't loud. It doesn't announce itself with exhaust sound or engine drama. It arrives quietly, electric, fast, and repeatable, until one day you realize the old trade-offs aren't laws of physics anymore. They were limitations of the tools we accepted. So the question has flipped. It's no longer, are Chinese cars good enough? It's this, if a vehicle can control its chassis like a motor, why are we paying premium money for suspension that still lives in reaction and compromise?